In this video, I'm going to demonstrate about a IoT-based water quality monitoring system. This is the dashboard for the monitoring system, and we're going to monitor temperature, pH, and turbidity. On my left hand side, we have a line graph, and on my right hand side, we have gauge. The gauge updates every second, where the line graph updates every 5 minutes interval. For the database, I have used a Firebase real-time database where the values are stored, which is sent from the microcontroller. For the turbidity, I have used this turbidity sensor, which is a laboratory-grade turbidity sensor. And if you look on the example code given by the manufacturer, the turbidity gives an output of voltage, which is between 0 to 5 volt, the reading. So the relation between turbidity and voltage we can see from this graph. When the voltage increases, the turbidity decreases. And from this picture we can say that when the turbidity increases, the water quality actually decreases. So having higher voltage and lower turbidity is good for our water. And for the pH sensor, again I have used a laboratory based pH sensor. The accuracy of this pH sensor is 0.01 plus minus at 25 degrees Celsius. To measure the water temperature, I have used a K-type thermocoupler. Let's have a look on the Arduino coding. For the K-type thermocoupler, I am using SN6675, which is a K-type thermocoupler. SN6675 is a K-type thermocoupler. 6675 is a K-type thermocoupler, and we have to use the Max 6675 header library, which is from Adafruit. To use the pH sensor, we need to calibrate it first, and for the calibration, the company already gave us some buffer solution. We are using pH 7, and the pH 7 will be reflected at 25 degrees Celsius. The probe is calibrated, but according to our room temperature we have to calibrate it. And from my K-type thermocoupler we are getting the temperature 32 to 31. Let's consider from 30 to 32 degrees centigrade. And to calibrate my pH according to this temperature, I have to put a random value here, like 3.2, 3.1. Currently 3.3 is the perfect calibration value. So I have to change every time the value and to look on the serial monitor and have a look if the pH is 7 or not. As we are using buffer solution, the pH 7 buffer solution, it should be 7, and at this temperature I am getting 7 degrees, so the pH probe is calibrated. And for the turbidity sensor, we are getting the voltage, turbidity voltage, but I wanted to transfer the voltage to something human readable or something like this NTU format, because they have also the graph for that one. To convert to that format, there is a formula. The formula is given here in the graph. I have used that one, the turbidity formula, and I am getting the turbidity value. So for 3.44 to 3.45 voltage, the NTU value is 2100 and something. It's changing. And for the pH, we can see this part is the pH code, and for the pH it's a 3.5 into pH voltage plus the offset value, which is really essential as we have to calibrate it here. So that's all for the coding part. We are getting the turbidity voltage, pH voltage, and the pH value. The pH voltage is 1.62, and the thermocoupler temperature is 31.00. Next, I'm going to demonstrate the practical of my system. So for the practical part, this is my setup. I have used Arduino Nano and Raspberry Pi. The Raspberry Pi is the master and the Arduino Nano is the slave. I have used Arduino Nano because this one have the analog pin. Raspberry Pi don't have. We can use ADC, but I have skipped the hassle for the conversion. And this one is the monitor where I can see the voltage is updating. The pH value is currently 6.97. It's going up because I've turned this off. Let's see the turbidity of the water. When we immerse the turbidity sensor, the voltage increases. When we take this out, the voltage decreases. Again, when we put the sensor in the water, the voltage increases. Let us measure the pH of the water. We have to put it in the water for 1 minute.